Okay, so what I want to do today, there are many ways to make a solution. One way is with dry ingredients. That's what we did last time. So I want to go over an example of that today. The other way is to dilute a concentrated liquid. That's what I'm going to do today. And they're sort of the same, but sort of different. So basically, when the stockroom buys acid, they never buy it already diluted. They buy the most concentrated they can get, and then they dilute it to whatever concentration we need to use in the lab. It's a very common technique. So let's go over the dry one first. When I say dry, that means I'm talking about grams. How many grams of blah, blah, blah do you have to add to get to this concentration? Or if I give you an existing concentration, how many grams of solute went into that? Okay, now remember there's solute and solvent. Solvent is the majority, solute is the minority. Okay, so looking at this guy here, what's the molarity of the following solution? Remember, molarity is moles per liter. Okay, so we've got 35 grams of sodium chloride in 345 liters of water. Okay, so grams is not moles, so we need to convert the 34.5 grams of salt, which is 58.44. Okay, that'll give us moles. Now, this is the same problems we did last week, so I just want to go over this again to refresh you. Okay, so that's equal to and that 0.59 moles is in 345 liters of water. Okay, so definition of molarity is moles per 1 liter. So now we need to divide the 345 into the 591. Okay, so that's big M again. And the big M, the other way to write it would be like this. Either one is acceptable. And it's 3 sig figs. Okay, so if I give you grams of something and volume of something, this is the calculation used. It's a 2-part calculation. You can, if you want, you can do all this in one calculation if you want. You can put this over that instead of the 0.59 and get the same answer. Yeah. Divided by 58, yeah. Yeah, what I'm saying though is also, you just want to put this there instead of doing 2 calculations, you do 1 calculation. So you can go 34.5 divided by 58 divided by 345, enter. You get the same answer. I would do it in 2 steps because to me it's clearer what's going on, but you can do it in 1 step if you want. Okay, and the other kind of problem is I'll give you a solution, 345 molar, and I tell you the volume, how many grams of sodium chloride are required to make that solution. So it's moles per liter. Now in this case, it's 345 moles per liter. Now, if we multiply that by the volume, the liters cancel, gives us moles. Okay, so whenever we have concentration, okay, so concentration times volume equals moles, because the liters cancel, leaves us with moles. Okay, keep that relationship in mind. Okay, so now we have moles, so let's go ahead and convert the moles to grams. So we have 19.6 moles, and we're looking at 58.44 grams per mole. So okay, so we had to put in a little over 1,000 grams into 3.54, or excuse me, a little over 1,000 grams and 5.67 liters, and we'll end up with this concentration. So those are the two types of dry ingredient problems you'll see. Okay, so are there any questions about these guys? Because when we're diluting, it's a kind of a different problem. I want to make sure this is okay. So let's go ahead and go on then. Okay. So dilution problems. Okay, so we're going from a bless you. So we're starting with a concentrated solution plus water. We're getting a dilute solution. Okay. Concentrated solution to dilute it down. We need to know how much of this to start with. And we need to know how much water to add. And that's, we end up with the volume of the dilute solution. So let me show you a little picture. So if I have 1 liter of concentrated solution, and I add 4 liters of solvent, that gives us 5 liters. How many, and if this is 9, 11, let's say 11 molecules of solute, and I throw in 4 liters of water, how many molecules do I have in the dilute? Yeah, we didn't touch the solute. All we did is we add solvent. So we still have 11. All we've done is we put in extra solvent or water in this case. Okay, does this make sense? Okay, so if I have 11 moles of solute, how many moles do I have over here? The same, 11 moles. Okay. So let's look at a dilution problem. Okay. So we want to end up with a 4.57 liters solution. Concentration is 2.34 molar. We want to start with this super concentrated solution. So how do we do this? Okay. So this is the concentrated now. So we need to figure out how many liters of this stuff we need to put into our diluted solution. Okay, so we arrived at that 5-liter solution up there because we started with 4 liters. Excuse me, we started with 1 liter of the concentrated stuff, and then we added 4 liters to it. So here, okay. So step number 1 is to figure out how many liters of the concentrated stuff we need to get over to here. So if we know the moles from which we start, we can figure the moles that we're going to end with, okay? Okay, so how many moles do we need in the dilute? Well, concentration times volume gives us moles. So we have 2.34 moles or moles per liter times 457 liters. Okay, so this is, so we need 10.7 moles from this guy to transfer over. Well, how many liters is that? Do calculation. right? This will tell us how many liters, or probably be milliliters, of the concentrated do we need to get into. Huh? What did I do wrong? Yes, right. Okay, good attention to detail. All right, so to solve this, what we're going to do is we're just going to, okay, so moles cancel, leaves us with the inverse of liters, which is the same as liters. Okay, so we're going to go 10, 7 divided by 24, 1. Okay, so we need 0.44 liters of the concentrated stuff to give us the number of moles we need for this. Okay. Again, it's concentration times volume gives us moles. Okay. So now there is, going back up here with the dilute, we're adding now 0.440 liters of the concentrated. And then we just fill in the rest with water. So 457 minus 0.44 liters, that's how much water we need to add. Okay, so we're looking at 4. Okay, so if we add so now our total volume is 4.57, but that includes the 0.44 concentrated stuff plus the 4.13 liters of water to bring the total to 457. Okay, did everyone follow me on that? I'm going to do a bunch of these, so don't worry. Okay, so the first thing you do, calculate moles that you need in your dilute. And the moles are going to come from the concentrate, but we don't know how much of the concentrate we need yet. That's the point of all this stuff. Okay, so concentration times volume equals moles. And then to calculate how much of the liquid or the liters, we divide the concentration into the number of moles, and that'll give us liters of the concentrate. The other way to look at this is you have the concentration side and the dilute side. So concentration times liters, and let's say sub C, standing for concentrate, equals the concentration of the dilute times the liters of the dilute. So you have 4 variables. So this is the one you need to remember for dilutions. Concentrate Now, this will not tell you how much water to add. It'll tell you how much of the concentrated stuff to add. So let's now redo this problem using this equation here. And all this does is equates to moles equals moles. That's where these come from. Moles equals moles. Okay. Excuse me. So the concentrated is 24.1 moles per liter. We don't know what the liters are, equals the concentration of our diluted stuff, which is 234 times 457. Now L equals, divide both sides by 24.1, so we have 234 . Okay, so the concentration cancels, leaves with the liters, and that'll end up with this equation gets it directly, but I wanted to make sure you understood how it flows. So all you need to remember is this. This is why it works. However, this just gives you the liters of the concentrated. It doesn't give you the total volume of water you have to put in there. So that's where we get the so this process is very straightforward. Once you kind of knit it out into kind of one equation. All right, so is everyone okay with this version of what I did? And this is much easier to remember too. But all those nice little beakers I drew is really kind of how it works on a concrete level. Okay, now this is important because this is what the titration lab is all about. Is we have moles of acid equals moles of base. And they're at neutralization, they're equal. But not gonna worry about that now. So that's a dilution problem. So you've got a dilution or creating a solution with dry ingredients. You create a solution with diluting a concentrated solution. So that's the essence of that solution stuff. You also need to remember how a crystal dissolves. Remember the qualitative aspect? We have the water hitting the crystal and pulling out the sodium and chloride ions and all that stuff. And then the three factors, remember the three factors that affect how fast that is done is temperature, physical agitation, and surface area. Okay, so are there any questions about this? I'm going to do some more examples. Okay. Now, why did it do that? So this is what the stockroom does. In fact, let's do one like for the stockroom. Okay, our next lab, let's say we need 12 liters of dilute and we want the concentration to be, and this is okay. So this is what the stockroom at Sac City did for me last week. I needed 12 liters of diluted. Oh, actually, it's not one. It was 0.1. Let me change that. I mean, this is, really a. Okay, so I needed 12 liters of this pretty dilute hydrochloric acid, 0.1 dosimeter molar. Okay, HCl comes in this jug, also called muriatic acid for pools, 24 molar. Very, very good. You take the top off and it smokes. It's pretty wild stuff. And it immediately will give you an asthma attack if you get in the way of that. The reason why I know is because I've gotten asthma attacks from dealing with concentrated hydrochloric acid. I lived in Woodland for 30-something years, and we had a giant pool. And I was experimenting with all these ways to chlorinate it. And one way was using hydrochloric acid concentrated. And man, I had to be really careful which way the wind was blowing. Because I got in the way of that stuff, because I'm prone to asthma attacks. Because I was little, I missed half of my school year because of asthma. So I'm very sensitive to stuff like that. So anyway, okay, so we need 12 liters of dilute acid at this concentration. And we're going to mix it from 24 molar solution of hydrochloric acid. So this is a dilution problem. Okay, so we're doing so the concentration of the concentration of the concentrated stuff times the volume of the concentrated stuff equals concentration of the dilute times the volume of the dilute. Okay, so what we don't know here is L sub C. So we know the concentrated, that's 24.1 times L sub C. That's equal to the dilute concentration times how much solution we need. So that's D. Okay, does everyone see where I got all those numbers? Again, just remember, you got to remember this. Concentration times volume, concentration times volume. Okay, so this L sub C will give us how much of the super concentrated stuff we need to add to get our final volume of 12.0 liters. Okay, so the concentration volume is going to be 4.98 times 10 to the minus 2 liters. Not very much. So I wouldn't do this in liters. I would convert this to milliliters. So that would be 4.98 milliliters. Let me show you how to do that. So we're going to take okay, so that's a concentrated volume. Now we have to dilute it up to the 12 to get our requisite amount. So that's when we subtract. Okay. So to get it up to 12 liters, we need to add to the 49.8 milliliters, 11.6 liters of water. So that's what the stockroom did just in my lab last week. Exactly that calculation. Yeah. Let's see, does this make? When you do the subtraction? Yeah, so did I. I can't even read. Yeah. My calculator did the subtraction right. I just didn't write it down right.
About 49.8 milliliters. Just gonna
Okay, so her question was, she wanted to know how I typically ask a dilution problem. I'm always going to give you the concentrated concentration. And then I'm going to give you the dilute concentration and volume. And you're going to solve for the volume of the concentrate. And you subtract that from your total, and you'll get how much water to add. Yeah.
In situations like this, you just what you round it.
I know it's 3 sig figs. 3 sig figs over here. This is kind of tricky to do sig figs, huh? Yes, but this is 3, and that's 3. So, yeah. And yes, you're right. It's 4. But you can see how concentrated it is. That's not very much. 50 milliliters, not very much, because that stuff is so concentrated. Okay, so that's officially the dilution way to create a solution. Okay. All right. Now you ask, is there some way we can practice this? Yes, there is. Okay, so we go to Canvas Files, Unit 5. There are lots of worksheets here on calculating molarity, calculating dilutions, acids and bases as well. We haven't got to that yet, but so there's a lot of practice here with answers. And I always give you the textbook text problems, and then and those only have answers with no setup. I always show you the setup when I give you the my worksheets. And here's some titration worksheets as well, which is the essence of the next 2 wet labs. Okay, so I'm going to finish off today talking about acids and bases, and it's going to be a qualitative discussion. And then tomorrow I'm going to get into the whole neutralization aspect of acids and bases, which is the essence of the titration you're going to be doing for their wet labs. And this dry lab this week is working out perfectly, so I get to have enough time to develop what we're going to be doing in lab. Yeah, I made it a take-home test. You must have come late. That's what we talked about. Yeah, so there's it's already there, and it's due next week. Okay, so yeah, I didn't hear what you said. What? I still didn't hear you. Speak up.
Is I need to exam today?
No, I postponed it. I made it into a take-home test. So I talked about that before you got here. So, oh, thank you. Yeah, it's there now. When you do the assignment, test 4, I'll explain what to do.
You dropped the worst grade we had for a test, right?
No,
You don't.
no, I gave you an opportunity to bring up the lowest test grade by doing an extra credit poster.
That's what it's about.
You know why I don't do that dropping test?
So people actually take all the tests.
I had some A students got A's in all first 4 tests, and they got a 0 on the last test. They'd still get an A. It used to bug me that they would just stop learning. You know? Just, so that's why I changed it. It's exactly why I changed it. Okay, so let's talk about acids and bases. So there are a lot of definitions. If you take 1A or 3A, you're going to find that there's about 4 ways you're going to talk about acids and bases. But they're not going to talk about the way I explain it. There's a Lewis Bronsted version. There's a whole bunch of versions how they treat what an acid is. Okay, so my definition, so you'll have a comfortable feel for what an acid is. Okay, an acid is it's a chemical that disassociates, that means comes off, and gives a hydrogen ion, hydrogen +1 ion. Anything that chucks this off is considered an acid. So there are 3 categories of acids. There is a strong acid, And these are the three strong acids I want you to know for this course. There are 7 total. Okay, this is hydrochloric, sulfuric, and nitric. And there are 4 more. Who's watched Breaking Bad? Okay, remember when it was early in it, they were trying to get rid of that body. How did they get rid of the body? In the tub with hydrofluoric acid. That's another strong acid, HF. And remember that it ate through the floor and the whole thing came flying through. Yes. Okay. All right. So they disassociate. %100%. So if we're looking at HCl, it would be so when I say 100%, that means that every bit of the molecule HCl goes to this. By definition, strong acids takes this apart. So each one of these, notice these are the hydrogens that comes off, and these will all go 100%. Now, sulfuric is kind of different because it has 2 H's that come off, and both of them come off. Only the second one doesn't come off 100%, only the first one. So this is called a monoprotic acid because that's a proton there, no electrons. So this is a monoprotic, diprotic, monoprotic. So this would be a mono, a diprotic, monoprotic. And that just refers to how many hydrogens dissociate. 1, 2, 1. Okay, so for sulfuric acid, because it's diprotic, that means 2 hydrogens can come off. Only the first is a strong acid. Now, if you have a strong acid, you also have weak acids. Strong acids, there are 7 of them. Weak acids, there are a couple million. Whole bunch of organic stuff are weak acids. There's tartaric acid, citric acid, aspirin is an acid. I mean, there's a whole bunch of it. Salicylic acid, go on and on. And all the fatty acids are all weak acids. So I want to emphasize again with the strong acids, there are nothing of the original left. Now with a weak acid, a weak acid, only a fraction of the hydrogen ions dissociate, and it varies a lot. Some hardly anything comes off, others a whole bunch comes off. And just because there's so many weak acids, the diversity of weak acids is horrendous. So then we have a weak acid. A good example of that would be Now, weak acids, notice I put the protons that come off with strong acids, they come first. Weak acids, they come last. And that's because going back probably 150 years or so, biologists mainly work with weak acids and chemists mainly work with strong acids. So the chemists came up with their convention and the biologists and later biochemists came up with their own convention. Just that's a problem in when I teach my organic class and my biochem class. Because when we get into the biochemistry part of the class, we have to talk differently. Like instead of reactions, they call it substrates. And instead of an activated complex, they call it a enzyme substrate complex. You know, they just use different names for everything. Okay, so and this is the one that comes off on the end. I meant say again now.
Right now, H4 CCOO. Would that be the strong molecule because it's separated?
It's written as a strong molecule, but it's not. They would just say, "Hey, who is this guy?" He doesn't know what to do.
Yeah, it wasn't written correct. Yeah.
Yeah. Okay, now I'm going to do the arrows a little differently in weak acids. Now there are two arrows with weak acids, a little arrow and a big arrow. What that symbolizes is the big arrow is pointing to this. That means with a weak acid, most is still tied up together and a little bit comes off. That's what makes it weak. Now there's some pretty strong weak acids like phosphoric acid. That's a triprotic acid. And it's when a first proton comes off, it's pretty strong, but it's still considered a weak acid. I get into a big debate with anyway. So it's important when you do the weak acids to have the two arrows. Big arrow means that there's more of this than that. A little arrow is a little bit of this. And there are literally millions of weak acids. There are so few strong acids. Okay, so then there's and then there is the opposite. Now, basically, whenever you think of an acid, you just check out the molecule. Are there H's present? Number one. Number two, will one come off or dissociate? If it does, it's an acid. So this has got four H's. These don't come off, only this one. Okay, so what if we only have these kind of hydrogens? That's called a non-acid. So that's methanol. It's got a hydrogen on the end. And it's got these three hydrogens here, but it is not an acid. This is an alcohol, and that's strongly bonded to that H. That's why it doesn't come off. Yeah. That means something's coming off of it. So here, the arrow, this little arrow means some of the H's are coming off. And because there's a big arrow going the other way, not all of them are, only some of them. And the strong acid up above, I only have one arrow. That means they all come off. And that's the differentiation between strong versus weak acid.
Is there a difference between non-acid and just base?
Yeah, we're going to do this whole thing with the bases in a minute. And it's the same strong base, weak base, non-base. Okay, so there's a lot of organic molecules that are not acids at all and have a lot of H's. Okay, so you've got to have the COOH though for the weak acid. If you just have a COH, it's not an acid, so alcohol. Okay, acetic acid is, the most common acids. Vitamin C, another common acid. Aspirin, another common acid. Okay, is everyone okay with this idea of H's coming off being defined as, okay. All right, so we can do the same thing with a base. Okay, probably most of you have heard of alkaline materials, like the difference between chocolates, for example. Processed chocolate means the chocolate beans were treated with lye. Who's had a tortilla, a corn tortilla that they haven't cooked? What does it taste like? Good, bad? Horrible. Yeah. Why do you think it's horrible? It's not cooked. What flour tortillas you can eat raw and they taste okay. The difference is the corn has to be treated with a strong base. It's called slaked lye. That's why when you cook them, the lye, residual lye goes away. Okay, alkaline or bases are bitter. That's why a raw corn tortilla tastes bitter. It's because there's residual lye left over in it. And the reason why they treat corn with lye is it softens the husk. Have you ever made trying to think of my Mexican cook is not here today. No, pozole. Okay. Anyone ever eaten pozole? Yeah. Okay. What's in pozole? What do you see white floating in there? Yes, exactly. Hominy is you take a corn kernel and treat it with base, and it swells up, and the husk becomes very tender. That's how they make that. But again, it's cooked though, so all that residual lye isn't there anymore, so they don't taste bitter. Yeah, first time I had pozole was in New Mexico. A good friend of mine lived there, and she took me around and showed me all the stuff. She said, "Gotta have pozole." So I had pozole. Okay, so a base is similar to an acid, only it's a different piece coming off. So instead of a H plus, we have an OH minus or hydroxide ion. So anything with an OH that disassociates is a base. And there's a number of definitions for that too. But this is the one we're using for our class. Easy to understand. Okay, and there are strong bases, weak bases, and non-bases. So strong base, 100% of the OH comes off. Like lye, sodium hydroxide. Potassium hydroxide. These are the two caustic chemicals you make soap with. When you take if you take 2B, Chem 2B, you'll make one of the things you do is make soap. So what you do is you take either one of these plus a fat like lard, and you cook it. And basically, the fatty acids come off because it's in an alkaline environment. You end up with the salt, and that's what soap is. That's what ivory soap is, actually. Okay, so strong base. %. Oh my God. Like ammonium hydroxide. It's a weak base. So if you ever clean in your kitchen and you want to get rid of something that's greasy, you want ammonia in your solution. For example, Windex comes with a glass cleaner and a grease cleaner. Make sure you read the label because they're not the same. The one with grease cleaner, still blue, but it's got this in it instead of a weak acid. And what this does when it hits water, it breaks down into ammonia ion plus OH. So you're really cleaning with a hydroxide ion when you're using ammonia. When ammonia mixes with water, it forms ammonium hydroxide. Ammonium hydroxide breaks down to that. And that's what dissolves grease. Yeah. How much is disassociated? So strong bases, there aren't very many. 100%. Everything turns into OH and at least one. Yeah. You can have ones that don't come off, but if there's one that does come off, correct. Correct.
So this one, like basically the H is left.
So if we had extra OHs here, and only this one came off, it would be considered a weak base. This one, yeah. But it's a weak base. So only a few of them did. Most of them are still attached. See that whenever you see the word weak with acids or bases, that means only part of them disassociate. Yeah.
So like, what you're saying is like if I had 1,000 particles, only 100.
Yeah. Yeah.
The other ones just stay NH4.
Exactly. Yeah. And that varies depending on the base. Some more come off, just like with weak acids. Some comes off. If it's a super weak base, only a few come off. If it's a strong weak base, a lot of them come off.
Individual level of one molecule of the NH4OH, that will have a chance of picking off 50% or 20%.
Yeah, and it depends on the stability of this. If this is fairly stable, more will come off. If this is not stable at all, hardly any will come off. Same with the weak acids. Exactly, it's all stability issue. Okay, so then we have non-bases. Let's look at methanol again here. So that OH will not come off. And it has to do with the stability of the CH3 plus. That's called a carbon cation. Very, very, very unstable. So this doesn't happen. So the OHs stay in here, hence it's not a base.
Will we have to determine if it's a strong, if it's a weak, or if it's a non? Like, will we be given the CH3OH and said, is this a strong one or a weak one or not?
Usually I just say, yeah, because you need more chemistry than what we had in here to determine that. But mainly, I just want to make sure you understand there are three classes. Ones that don't disassociate, some that go 100%, and then in the middle is the gray area.
Like,
You
if
know,
anything, we're gonna be like, here's a strong base. What does it go to? Kind of a thing.
so when we're in the titration lab, we're using a strong base and we're using a strong acid. Only the acid is a powder. It's kind of interesting. That's what we're doing next week.
Okay.
Then the week after that, and we use that to figure out our concentration of the NaOH. Then we use our standard, it's called standardization, standardized OH for the following week to go against vitamin C tablets.
Okay.
So, okay, so, and I want to leave you with this interesting little molecule. H2O. Most common compound on the earth, and it is both an acid and a base. So an H will come off and an OH will come off. Not very much, but it happens. So if we redraw H2O as H like that, we end up with that. Because it's both an acid and a base.
Term neutral.
Mm-hmm. Yes, she said you use the term neutral. Neutral means you have equal amounts of this and this. If they're equal, it's quote unquote neutral. And then there's something called a pH associated with which pH 7 is neutral. pH is a measurement of the strength of your acid. The lower the number, stronger it is. Higher the number, the weaker it is. And P, the little p stands. We don't get into this. I'm not allowed to teach this in here. Now, the first time I taught this class, I said, well, my students need to know about logarithms. They said, no, because we're not doing pH. Let me show you what pH is. Little p, extremely important. It's lowercase. Okay. You don't have to write this down, but it's the negative logarithm of the hydrogen ion concentration. There's also POH, which is the negative log of the OH concentration. So that's what pH is. And they thought the math was, who's done logarithms? Yeah, I mean, everyone's done logarithms. I don't know. Anyway, do a lot of pH stuff. So if you have pH, you automatically know concentration. You take the anti-log, negative of the anti-log, and you end up with the concentration of the H or OH or whatever. And then at pH 7 is officially neutral. Okay, so again, pH is just a measurement of acidity. Lower, and what's weird about it, the lower the number, the more concentrated. It has to do with this here, because it's the negative log. So when you get a smaller negative log, it's bigger. I was a math major, so I like this stuff. All right, that's what I want to cover today. So we're doing the dry lab. No, if you look on the schedule, the right, it goes 3 o'clock in the morning.
Okay.
Yeah, so I covered this before you got here. No, it's fine. Basically, also test 4 is not tomorrow, it's take home. And it's available. There's a whole bunch of people asked me to postpone it, and I said, doesn't matter to me.
The stoichiometry that you posted in file.
Say again?
Are we doing the stoichiometry that you posted in the files for our lab test?
Yes, that's the dry lab. The one that says stoy, right? A dry lab stoy. Yeah.
Well, think about the test I just checked. Maybe you click on 4.
Yeah, don't click on it. Right. Download it first. Because it's coded. Download it and then and then it'll prompt you for a code when you try to open it.
How do I not? How do I-
I tried to open it.
Right.
Yes,
Right.
the password.
If you go to assignments, test 4, it'll tell you the code. It's 2483.
Okay.
But because some people were going to be away and they needed, that's why I did that. So, which is nice because I ended up doing it anyway. Okay, so, but download it first. Canvas does not like coded Word files. Huh?
Was lab 11?
No. If you look at the lab schedule in Canvas, today we're doing a dry lab. Did you do the write-up for that?
Yes.
Cool. You're a week ahead.
That's all that.
Yes.
You're submitted. Some say that it's just not really due date or something.
Yeah.
Okay.
I've been trying to keep up, but I have tons of,
I didn't even care. I didn't know if.
Yeah. but I might have, if you turned it in late, well, if you turn it in legitimately late,
Yeah.
and I graded the whole class, sometimes you'll get a 0 or some penalty.
Yeah.
But because I keep changing things around, I don't know again. Unless it's like 2 weeks late.
But it's due date.
Oh,
It's
good.
like wasn't changed on. But
See, to make a
it's
class,
still in there.
make a class in Canvas, you have to take an old,
Saying,
yeah, and the old due dates are still there.
yeah,
Then I have to remember to update the due dates.
okay, yeah. 'Cause I think my lab 11, the one I just turned in, it says that it's an old due date.
So it's like 1 year later, it's in the board, lab 11.
And I think my lab class on Saturdays is.
I know, but I just changed this.
That's all, technology.
No, you're fine.
Okay. Okay.
Couple questions. So today's that lab and I already did it, so I don't have to go to lab, right?
Correct.
Okay, and then second, on Canvas, it says that there's a test final on the 16th and the 17th. What is that? Why are they recording?
Oh, I don't know. I mean, it's a take-home test.
Yeah,
So, I don't know why I have two. It'll be due on the 17th. Anyway.
okay. And then I
I need
have,
to change that right now, actually.
and then tomorrow we're gonna be doing what exactly?